Hao from Guanyun Lab, Zhejiang University. This is my first time at UIST, and I'm happy to share our new work, MagneDot, Integrated Fabrication and Actuation Methods of Dot-Based Magnetic Shape Displays. We focus on smart materials and their implementations to expand the forms and mechanisms of the tangible shape-changing interfaces, while making it more accessible to the general audience. Let's start with the background on material-driven tangible shape-changing interfaces. Among existing studies, soft materials are used to achieve pneumatic actuation. And for 4D printed objects, their morphing processes are often triggered by heat. Electrostatics can also be utilized to make things morph under control. These actuation methods are effective for making shape-changing UIs. However, all technologies have limitations sometimes. For example, pneumatic interfaces require constant air pressure and tubes. 4D printing relies on irreversible morphing mechanisms, so adjusting them needs reheating or manual work. And electrostatic requires external electric charges. We found that magnetic materials allow for contactless, instant actuation, and flexible shape-changing effects, while they are power efficient. These unique properties make them suitable for creating more accessible, tangible interfaces. Apart from using off-the-shelf magnets, recent studies have shared interests in magnetic rubber. Its magnetic distribution is editable. Magnet plotter, magnet shape, and mixels provide tools to directly write magnetic patterns and introduce shape or information display. A few studies have used manually fabricated hard magnetic soft materials. For example, flux paper is a type of self-aligning magnetic paper. Magnet I/O used these soft composites to create haptic feedback. Especially in EPOL memory, the shape-changing ability of this material is explored and showcased more flexibility. As an emerging topic in material science, HNSM showcased new effects of deformation, as well as applications in robotics and biomedical engineering. As shown in these videos, actuated by a changing magnetic field, HNSM makes it possible to swiftly and reversibly display shapes and information. We believe they are powerful, small materials for creating tangible, morphing UIs. However, the field of HCI is lacking available methods for people without a material science or engineering background. We are facing the following problems. First, designers and users in our field usually lack domain knowledge. Thus, designing a magnetic soft interface with the desired shape is beyond our imagination. For fabrication, to ensure an effective result, existing research in material science relies on sophisticated instruments. Without custom fabrication methods, excessive labor is inevitable, especially when we have to assemble numerous parts. Finally, it's difficult to precisely control the shape-changing behavior. For easy fabrication and manipulation, we introduced a dot-based design scheme that enables magnetic structures to individually control a given shape display pattern. The dots are connected by non-magnetic cyclone, forming a complete structure. There are two types of dots, the anchor dots and the trigger dots. During the actuation process, the anchor dot is attracted by the external magnetic field and fixed on the platform, while the trigger dots are elevated by the repulsive force, which is performed by the actuation magnet underneath the platform. The magnetization process is involved using a hard magnet. It is performed by placing the hard magnet in proximity to the target dot. Here are examples of the shape-changing process enabled by MagneDot. We provide a series of design elements to showcase a possible way to design MagneDot patterns, including circular and rectangular. So we ask ourselves, how can we achieve the best shape-changing results with most affordable materials? To attain the ideal result, we started by investigating the material composition and the MagneDot configurations. We tested the magnetization results for different mixture ratios and dot dimensions to achieve sufficient magnetic flux density and uniformity. As a result, we recommend 2.5 parts of neodymium powder to 1 part of silicon. The ideal dimension is 3 millimeters in diameter and 1.5 millimeters in height. Here we showcase the shape-changing behaviors of 2 samples. As the magnet approaches, the group of trigger dots is elevated and it flips in a second sample. Now let's focus on the fabrication of MagneDot. Our hardware is based on an FDM 3D printer and equipped with custom add-ons such as extrusion system and a magnetizer module. The fabrication workflow begins with 3D printing mode. Then we install the extrusion module and execute the extrusion process, which involves filling the mold with the mixture. After the MagneDots are cured, we swap the extrusion syringe with a magnetizer module. The magnets directly write the polarity of MagneDots. During the process, we manually reverse the magnetic pole to switch between the anchor dots and trigger dots. After magnetization is finished, we replace the magnetization module with the extrusion module for silicon extrusion. MagneDot shape display can be removed after it is completely cured. To make the fabrication workflow more approachable, we developed a design tool in Grasshopper to assist this process. After we import the 2D design pattern to Grasshopper, it generates the G-code for extrusion and magnetization. In the design tool, we also develop the actuation control function. We provide 2 ways of control, curved-based and point-based. After setting the actuation paths or waypoints, we can adjust the travel speed of the actuation module and the number of cycles. Export the G-code, and we can change the hardware add-ons for interacting with these shape displays. The video shows the automated actuation processes of Venus flytraps and a windmill. In addition, we also designed a manual control toolkit to fit people's pockets so that everyone can experience the shape changing with minimal setup and preparation. Now let me demonstrate the applications of MagneDot. The flytraps can be used for storytelling. In nature, a flytrap has a pair of lips. When a bug approaches and lands on a flytrap, it triggers the lips to close up and tracks the bug inside. Here is an information display. The magnet underneath the platform writes the 4 letters of UIST, and it can be erased and rewritten. What's more, the ring application shows the potential of MagneDot on jewelry. Finally, we made a soft robot, and it performed the task of retrieving the white plastic object from the glass tube. Small MagneDot structures can traverse through narrow spaces. We've also explored several interactive games. The first one is a manually controlled pinball. The second game is a fishing game. The MagneDot pieces move to mimic the aquatic animals, such as starfish, and the player controls the fishing rod and catches the creatures. In the last game, we represent the concept of a digital game with a tangible accessory. The MagneDot animal controlled by the player cross toward the star displayed on the screen, and the player will acquire a game credit. In the future, we envision the application of MagneDot becoming capable of both shape input and output, fully leveraging the advantages of magnetism, softness, and flexibility. MagneDot will be a more functional interface. We also plan to add more features to our design tool, such as design assistance and shape change simulation preview, to further improve the usability and accessibility. What's more, we are exploring the application of MagneDot in wearable and haptic devices. We aim to expand the library of sub-materials, seamlessly connecting our bodies, interfaces, and living environments. We have brought some gifts. They are fly traps from our application collection. The number is limited, so please feel free to reach out after the paper session. Also, we are having a demo this evening from 6 to 9 p.m. in a multi-purpose room of the August Wilson.
All right, let's give a round of applause to our presenter. And for Q&A, you can either come to the mic or I can run the mic to you.
Hi, Roel Vertigal, Human Media Lab. I love this work. Thank you so much. Could you explain a little bit more? It's maybe a newbie question, but how do you actually provide the magnetization in the case of the display, where it's on a display? Is it underneath the display, or how does that work?
Could you please repeat?
The animation on the display,
Yeah.
right? Where is the other magnet, basically?
It's under the platform.
Under the platform.
It can be controlled by the 3D printer.
Ah, okay.
Yeah.
3D, so there's a 3D printer underneath the display.
Yeah, or we can manually hold the magnet and
Okay.
control it.
Okay, thank you so much.
Thank you.
Hello, my name is Jack Foreman. I'm a PhD student at the MIT Media Lab. I really love the work. Thank you for presenting it. I guess the question that I have is if you've explored other flexible substrates beyond silicone. For example, maybe you could 3D print this onto fabric and combine it, so maybe you have something that as you wipe your hand across your magnetized fabric, you get a dancing ring.
Yeah, hi Jack, it's very cool. Thank you for your advice. And we are trying to explore like more MagneDot on our skin and something like that. Thank you.
Cool, I look forward to it.
We probably have time for one more short question. People can feel free to come to their poster after.
Thank you for your presentation. I may lost between the presentation, but you used the magnet to move the your MagneDot,
Yeah.
but then it moves automatically to move the cube outside the tube. I was wondering how you made the MagneDot move inside the tube.
Thank you for your question. I think it's about this application. Yeah. Actually, it is controlled both automatically and manually. When the robot is like, maybe I will repeat again. In this state, it is controlled like using our 3D printer, or you can manually control it under the platform. Yeah, and when it needs to like flip to the other side, maybe we need to control it above the tube, and it can go through. Yeah. Thank you.
All right, let's give